Hey all, this is Mr. Yeager. We are finishing up our unit on waves and looking at light and sound today. All right, so we're going to be checking out light in terms of looking at what's called the electromagnetic spectrum, just going over what type of wave light is, as well as talking a little bit about color. And then we go into sound and basically look again at what type of wave it is and look at things like pitch, the Doppler effect, and sonic booms, okay, shock waves. So that's what we'll go with. Here we go. So light. Light is an electromagnetic wave. Okay? It is an electromagnetic wave, which means light can travel through a vacuum, which that's an excellent thing, okay? Because obviously we wouldn't have any light on Earth if there was no sun, and the light wouldn't be able to travel that way. All right? So that is important. Light is an electromagnetic wave. It doesn't need a medium to travel through it, okay, in order to travel. There are many forms of light. What we're all used to is what's called visible light, but there's lots of different types of light out there, and it's all on what's called the electromagnetic spectrum. All of these different types of waves are technically forms of light. So radio waves, microwaves, infrared, visible, ultraviolet, X-rays, don't worry about soft and hard X-rays, and then gamma rays, they are all different forms of light. It's just we can only see in this small section called visible light. All right? So, some things you got to be able to do with the EM spectrum, if it's given to you, is going back to those relationships of frequency, wavelength, and energy. We're interested in frequency, wavelength, and energy. All right? And possibly having to rank different types of electromagnetic radiation. So if we look at this, we basically can look at the edges, radio waves and gamma rays. If we look at radio waves, they have long wavelengths. So they have a high wavelength, they have small frequency, and what's energy directly related to? Frequency, so they have low energy. So down on this end of the EM spectrum, we have high wavelength, small frequency, small energy. On the other side, they have small wavelength, high frequency, and therefore high energy. So gamma is the most energetic and dangerous form of electromagnetic radiation. We talked about that all the way back when we talked about radiation. All right? Radio waves are the least dangerous. And so if I have to rank these from highest to lowest energy, I just have to go from gamma back to radio waves. So gamma is the highest energy, followed by X-rays, followed by UV, ultraviolet, followed by visible light, infrared, microwaves, and radio waves. So that's the thing. If you study just one side of the EM spectrum, you know the whole thing all the way down to the other side. Okay? So just pay attention to that. Remember that wavelength and frequency are inversely related, and then energy and frequency are directly related. And you can figure these out all the time. All right, so how do we see color? We see color based on what type of light is reflected. So when I say my shirt is red, it's red because it's reflecting the red light and absorbing all other colors around it. You only see what's reflected. That's the thing. You're only ever seeing reflected light. Okay? We have basically coming from light bulbs and stuff like that, or the sun, we call it white light. Okay? Light from light bulbs and the sun is called white light. What white light is it's a mixture of all of the colors. I don't know if I'm able to do this or not. I don't think I have all the colors on this thing. But basically white light is where there's red wavelengths, there's yellow wavelengths, there's orange wavelengths. I don't have orange though. There's green, there's blue, there's purple, there's that other color indigo. All of these things mixed together you see as white light. You can't see the colors separately. But then there's dyes and other things in your shirts, on the walls, on the floors, on objects around you that either absorb some of these colors or reflect some of these colors, and what is reflected is what you see. Okay? That's the big thing. What is reflected is what you see. So white objects end up reflecting all colors. They absorb no colors. That's why we say White is something that can be cool in the summer because it's reflecting all the light off of you. Black objects, they reflect no colors. They absorb all the different colors. So that's why we say don't wear a black shirt or black outfit in the summer because you'll be hotter. Again, objects only reflect the color that they are. If they can't reflect the color, the object will appear black. A red shirt. So what we'll run into is what happens if you put a color under a different colored light. Like I said, objects under other lights. All right. So again, an object can only reflect its own color. So if you put it under a different color light, it's going to appear black. If it can't reflect the color that it wants, it appears black. So a red shirt actually under a blue light appears black. All right. And that's what this is trying to show you a little bit here. So I have a red strawberry, a yellow lemon, and a green apple. If I shine this under red light, the strawberry still appears red. I'm not worried about the lemon because that's actually something different, but the green apple appears black. If I shine it under green light, the strawberry is now black and the apple is now green because that's what it reflects. Under blue light, everything will appear black because they can't reflect blue. It turns out yellow, just to mention it, yellow is a mixture, it is something where it reflects red and green back. So that's why the lemon appears red under red light. It appears green under green light, but it can't reflect blue. It pulls in blue, and so it appears black under blue light. So again, what you see in terms of color is what is reflected. What is reflected. All right. So that's it for light. Okay. So light EM waves. If I give you the diagram, highest energy, highest frequency, lowest frequency, highest wavelength, lowest wavelength, and then be able to talk a little bit about why we see certain colors. Okay. Again, it's what is reflected. If it can't reflect it, it appears black. So moving on to sound. Sound is a compression longitudinal wave. It's a compression wave. So that's the one where it's like an accordion, okay, where you're squeezing it together and then expanding it. Sound is also a mechanical wave, as I mentioned in an earlier lecture. It's a mechanical wave, which means you have to have a medium. And as with any wave, it carries energy. Now in class, we then do all sorts of little fun hearing tests and things like that to kind of go through it. Skipping that, all right? When I say sound has to travel through a medium, okay, this medium can be gas, liquid, or solid. The thing is, sound will travel faster through one of these states of matter, faster than the other ones. Which one? Solid is the one that sound travels fastest through. Why? Because it allows the objects, the particles, to be very, very tight together. All the particles tight together. So if you vibrate a little bit, it immediately smashes into another particle, okay? You got to think again of a solid all very close together. All right? And so if I hit the solid, this one's right next to that one, which is right next to that one, and they're able to carry that energy through the object very, very quickly. So sound travels fastest through a solid and actually slowest through air. That always confuses people because we hear sounds most often through the air, but it's actually traveling slower than solids or liquids. Sound cannot travel in a vacuum because a vacuum means there's no medium. A vacuum is empty space. So if you go to outer space, and you yell, nobody can hear you yell. Okay? You need to have some sort of particles to vibrate in order to create a sound. All right? So, there you go. So fastest medium is solid, then liquid, then gas. It also turns out that sound travels faster at high temperatures versus low temperatures because, again, the particles are moving faster. And the sound travels faster at a lower altitude than higher altitude because as you increase altitude, you decrease the amount of particles present. That's the whole idea where you can get oxygen sickness by going too high. You don't get enough oxygen. The air gets thinner. Pitch. Pitch is looking at how high or low the sound is. So if I have a very low pitch, it's a very, very low pitch, okay? That is talking about the different frequency of the vibration. So a low pitch is a low frequency. A very frequency. Yep, I'm going to make myself sound like pretty silly there. So pitch just depends on the frequency. High frequency, high pitch. Low frequency, low pitch. There you go. Higher pitch, higher frequency. Lower pitch, lower frequency. All right. It turns out humans can hear from 20 to 20,000 hertz. 20,000 hertz would be an extremely high-pitched sound, one that probably will not feel pleasant. 20 hertz would be one that just almost sounds like it's just a little bit of like a rumble. Okay. There are what we can call ultrasonic or infrasonic sounds. Ultrasonic basically means that the sound is above what we can hear. So obviously dogs and bats there's certain animals that can hear higher ranges of sound than we can. And then there's what's called infrasonic, or below what we can hear, below 20 hertz. And this is what earthquakes and machinery sometimes vibrate at, where it's one of those things you can't hear them vibrate, but you can sometimes kind of feel that vibration. That leads us to the Doppler effect. The Doppler effect, as you know, is that sound, okay? It's created due to a change in frequency caused by motion. So in order to have the Doppler effect, something has to be moving. Either you or the object that's making sound, one of those two things has to be moving. You can both be moving, that's fine. But the Doppler effect is a change in frequency, therefore a change in pitch, due to the motion of the source of sound. Okay? The faster the source moves, the greater the Doppler effect. In other words, the greater change in frequency we hear. So that's why when you have a police car go by, the person that is in front of the police car where it's passing by will hear a higher frequency, a higher pitch, while the person behind it will hear a lower frequency, lower pitch. It's just basically where the waves are either compressing or expanding behind the object. All right. There are different uses for the Doppler effect. I'll come back to that later. This is a good animation, another good video you could go to on this website to go through, on this particular website, to find out more about Doppler if you'd like. Again, what I'm looking at here is how we usually illustrate the Doppler effect. What I'm trying to show you here is there's a little cricket right in the middle. If I have two people standing basically equally far away and the cricket doesn't move, they both would hear the exact same pitch of sound. Doppler effect is not about volume. It has nothing to do with volume. Obviously, if the object's closer, it'll be louder than farther away. That's not the Doppler effect, though. So right now, there is no Doppler effect in that one. But now the cricket starts moving. As it keeps moving, the person at B will hear a higher pitch because the waves are all compressed together. So they'll hear a higher pitch sound, while the one that's the cricket's moving away from will hear a low pitch sound. High pitch, low pitch. All right, so again, this is just another good picture of it. Person in front of the car would hear a higher pitch, person behind the car would hear a lower pitch. That's the sound at racetracks and stuff like that. For you in the car, you don't hear any change because you're moving with the sound. You're moving with the car itself, so you don't hear any difference. So again, as the object moves towards you, the waves get compressed. You'll hear a higher frequency, a higher pitch. As the object moves away from you, waves spread out, lower frequency, lower pitch. There's all sorts of use for the Doppler effect. We use it for the Doppler radar system for weather. It helps us, this is how we can predict how storms are moving through or how possibly the storms are going to be approaching us. Again, there's other factors involved. It basically just helps us find the speed of the storm and how dense it is. Okay? Radar guns, ultrasounds, all these things use Doppler effect as well for their use. Okay? There's also a Doppler effect for light that I always like to mention. We call it, though, the blue shift, red shift of light. Blue shift is when the object's getting closer because blue is actually a higher frequency than red. So that's where the waves are getting closer together. Red shift shows you the object is getting farther away. So astronomers use this to figure out which way objects really far away in space are orbiting, whether they're getting farther away from us at this time or getting closer. They'll see what's called a blue shift or red shift in the light spectrum. The last thing I like to share is what are called shock waves. Shock waves is basically where something is now traveling supersonic. So this would be the sonic boom, a jet flying above the speed of sound. Would create what's called a shock wave behind it. It's a conical shaped wave that's produced when you have supersonic speed. All right, you have to go faster than the speed of sound, and it'll create something called a sonic boom. Okay, that's where that huge compression set of air passes by your ear. It creates a boom sound behind it. Okay, so again, this is just showing you what objects would look like as they traveling different speeds and making sound. You got your stationary object, you make concentric circles. If you're moving slower, you're going to the left, but the waves in front are getting tighter. So again, on one side, you'd hear a higher pitch. Okay, you'd hear an increased pitch. Back here, you'd hear a decreased pitch. As you get faster, these waves compress even more. If you go supersonic, you make a conical shape to it. And then basically, I just have some different pictures and videos that I share with the students. Okay, but that's it. All right, thank you very much.